everyone. We just finished talking about inductors, so let's put them in AC circuits. That's what we're going to do in this section. On the left, we see that there's an inductor, there's an AC source. What happens in this case is that the current in the circuit is impeded by the back EMF of the inductor. So what this means is that the current is continuously changing because of the AC source. It's going this way, and then it's going this way. It keeps going back and forth. So we learned in a previous section that when the current changes in the inductor, it produces a back EMF. It produces a voltage to oppose this change. So that's what we call the back EMF of the inductor that is opposing the change in current. What happens when you have an inductor in an AC circuit is that the voltage is leading the current. We can see this in the graph over here. So over here we have zero current. It's changing from a negative to a positive. That's a very big change in current. It's changing directions. In this case, we have a maximum voltage that is induced, a maximum back EMF on the inductor. When we have a maximum current here, at this instant there's no change in current. It has reached its maximum. When there's no change in current, then there's no voltage. So you can see that the voltage and the current reach their maxima at different times. They're not in phase. We say they're out of phase. And we say, in this case of the inductor, that the voltage leads the current. This means that the maximum of the voltage occurs before the maximum of the current. Let's look at this question. In the circuit represented by these graphs, the current blanks the voltage. So if the voltage leads the current, that means that the current lags the voltage. So this was just rewording what we saw in the previous slide. So whenever you have an inductor in an AC circuit, that inductor has a reactance, and you can think of the reactance as the effective resistance of the inductor in that AC circuit. So when your inductor produces a back EMF, that back EMF is opposing the current. So the inductor has an impeding effect on the current. Whenever something impedes the current, we like to think of it as a resistance, but because this is an inductor, we call it a reactance. But for all practical purposes, just think of it like resistance. It makes it easier. Now, this has a symbol X sub L for inductive reactance. It does have the units of resistance, which is ohms. The difference about this versus the regular R that we're familiar with is that the reactance of the inductor depends on the frequency of your AC source. You can see that it depends on 2 pi times frequency times the inductance. We can replace 2 pi f with omega just to make the expression look a little bit more simple. So what this shows is that as you increase the frequency, the reactance increases. This makes sense because when you increase the frequency, what that means in your circuit, it means that the current alternates back and forth a lot faster, right? More cycles per second. So if you have a very big change in current, there's going to be a lot more back EMF, a lot more impedance to the flow of current. So there's going to be a lot more reactance when there's a high frequency. The good thing about reactance is that we can think of it like resistance, and if we're trying to find the voltage drop across our inductor in the AC circuit, we can still use Ohm's law. Ohm's law used to look like this for a resistor. The voltage equals the current times the resistance. Well, we can find the voltage across the inductor by doing the current times the reactance, the inductive reactance. So it's just plug and chug. If you have the reactance and the current, you can find the voltage across the inductor.